Hi, this is our elevator pitch for dynamic right sizing for power proportional data centers. I'm Tejas, and my group consists of Gaurangi, Varun, and Dante. Right. So data centers are the backbone of modern digital services, but they come with a major downside, which is high energy costs. Even during periods of low demand, servers consume nearly 50% of their peak power while idle. This inefficiency is driving the need for a power proportional data center where energy consumption aligns with workload demand. So, what's our solution to this? Our solution is dynamic right sizing, which is a strategy that dynamically adjusts the number of active servers based on real time workloads to reduce energy waste and optimize performance. If you look at this graph over here, we can see that for servers that are idle versus they are at any other workload, the power consumption is basically the same for all of them. And that is the problem that we're trying to solve. That even if the server is idle versus it is at 100% capacity, it is at the same power level. So there is some sort of optimization that we could do. We are trying so that some servers which are idle go into this hibernate state over here and use almost negligible energy. So what is dynamic right sizing? It is a game-changing approach that makes data centers power proportional. It works by turning idle servers off or putting them into sleep mode during low usage periods and activating them as demand increases. This ensures energy efficiency while maintaining responsiveness. For example, let's say let's say take the example of Black Friday. So during Black Friday, Best Buy would need more servers so that they can handle the high traffic coming in and they can minimize the delay costs. And also during off-peak hours, which is something like midnight to 6 a.m., servers are scaled down to save energy without compromising user experience. So for the general model, the entire objective is minimize total cost, and total cost is operating cost plus switching cost. So operating cost confers to this FTXT over here at a time t, and this beta is a switching cost coefficient, and xt minus 1 is the cost of turning servers on or off. So how does this model apply to the real world? So basically, this can be divided into two parts, either flexible QoS services, which is the Best Buy example I just gave, and the hard SLA service, which could be understood by taking the example of Charles Schwab, which is a trading platform where ultra low latency is critical. Our model ensures enough servers are active to meet strict latency requirements while optimizing energy costs. So something that is already in place is receding horizon control algorithm. But the problem with this is it has a high dependence on time periods and it cannot work well without future workload knowledge. While the LCP algorithm, which is what we are proposing, is robust without any time period knowledge.
Optimal offline algorithm is the base model which is used to get to the approach that is proposed by the authors. So the optimal offline solution refers to the best possible way to schedule the number of active servers in a data center. However, this is only theoretically possible as it requires the entire future workload knowledge in advance. This solution is characterized by using upper and lower bounds, and the number of servers are calculated in reverse. What this means is that the key takeaway of the solution is that it is lazy in reverse. This means that the servers are changed only when it's absolutely necessary, and it usually stays constant between the upper and lower bound. The proposed solution by the authors is called lazy capacity provisioning algorithm. It provides a realistic solution to this problem of dynamic scheduling, and unlike the offline optimal offline algorithm, it goes forward in time. It has no knowledge about all the future workload. It instead uses a prediction window which is arbitrary and and this window is used to calculate the local maxima and minima to define upper and lower bounds to calculate the number of optimal active servers. So with LCP, only the operating cost for a prediction window is known, and the equation to represent the number of active servers in LCP is given by the number of active servers at t minus 1 which is then bounded by the lower and upper bound. The LCP algorithm is three times competitive to the optimal offline algorithm. What this means is that even in the worst case scenario, the LCP algorithm will perform at the most three times worse than the optimal offline algorithm. And this optimal offline solution is considered to be the benchmark or the best possible solution for finding the optimal active number of servers. One more thing to keep in mind is that the competitive ratio is independent of the window size W. So choosing an arbitrary window size does not affect the competitive ratio. Thank you.